Greetings, chemistry students. It's Mr. Gopal, and I'm here to talk to you about the Unit 7 lesson on potential energy diagrams. Now, this lesson is focused around the simulation, but what we're going to do is we're going to come back to this diagram. I'm going to quickly show you the lesson, and that is from Unit 7. It's lab number 22. It's the potential energy diagram. And they have a simulation where you can go through an actual chemical reaction that can be plotted out by a potential energy diagram. Now they call it a diagram, but I like to call it a graph because we can read it like we read graphical things with an X and a Y axis. The Y axis tracks the amount of potential energy in the reaction at any given point. And we call the horizontal axis the reaction coordinate. That's a fancy way of saying that I'm tracking the reaction over time. Now, the interesting thing about this is I can read it from left to right, or I can read it from right to left. All right, a little bit of that. If I'm reading this one from left to right, I'm actually going to annotate my own document to go over this. From left to right, we see, number one, the first thing is that we see a loss of energy. All right. If I'm thinking about this right here, then I can say this point is higher than this point here, which means that there has been this much loss of energy between, we're going to talk about, that's labeled by letter D, the change in energy from beginning to end. We're going to put a name to that change shortly. But we know that from left to right, if I read it, there's loss of energy, or energy is being released, okay? And that happens when a bond is formed. You can see at the bottom of my document, I have that listed out. I also have some other terms listed out. But before we get to those other terms, I'm going to say if we read this from left to right, that means it's an exothermic reaction. Exothermic. And that means that energy is being released, all right? So we know, we see a loss of energy. That means energy is released through the chemical reaction. Finally, we know because of that, a bond is formed. And this means we're looking at an exothermic reaction. Okay, so all of this I can just tell from the graph. Now, if I were reading it from right to left, I'm going to annotate that all in blue now, that would mean that a bond is being broken, and so energy is being absorbed. And I know that this is an endothermic reaction. All right, endothermic. Okay, next to that, I'm just going to write in a text box. Endo means in. And in other words, energy is taken in. And down here, exo means out, because energy is released. Okay, so this is the first thing that we can tell from a potential energy diagram. Depending on what direction we're reading it in, we can say whether it was an endo or an exothermic reaction. And this is important to know because you'll know whether the products of your reaction have more or less energy than the reactants of your reaction. And the other thing you can tell is that what's going on is a bond being formed, is a bond being broken. Now, the way that we remember that, I'm just going to clear this here, make sure that you got it down. The reason we know that, or the way that we can remember that, is by hanging on to our handy acronym, and that is BARF. All right. BARF stands for, and I've hinted at it in number 3 here, BARF stands for broken, absorbed, released, formed. All right. In the first instance, if a bond is broken, energy is absorbed. Therefore, I'm talking about an endothermic reaction, right? Because we know in an endothermic reaction, energy is taken in. If I'm talking about energy being released and a bond being formed, I'm talking about an exothermic reaction. Now, it might seem strange that energy is released when a bond is formed, and that energy is absorbed when a bond is broken. I like to think of, let's say that I have a hammer and I'm like breaking a tablet. Let's say that I have a pill that I have to take, but I can't take the whole thing. I'm going to break it into pieces or something like that. Now, I'm breaking it up, and that takes energy going into it. So I whack my hammer down on the pill, it breaks into pieces, it has absorbed that energy, and now that's why it's broken into many different pieces. And that helps me understand why that's an endothermic reaction. It takes in energy to be broken, and in the act of forming a bond, it gives off that energy. So if I bring it all together, it will give off that energy. All right, that is one way to remember. So I'm going to clear this as well. Now we know what's going on, and our next task is to put some vocabulary to this, and I have a little key for you. So we know that A, or this line right here, represents the heat of reactants. All right, that's my heat of reactants right here. Actually, I'm going to undo that, redo that circle so we can circle the other things, and I'm not covering anything by accident. All right, on the other hand, if I'm talking about the heat of the products or the heat of what I end up with, I'm going to circle that in blue. And that is right here. It's my heat of the products. Okay. And now I'm going to go directly up to D, and I'm going to circle that in green. D is very important because that is the change in energy from beginning to end. We can see here that we start at this level of energy. I'm marking it in green, and I end up at this level of energy. And the difference between the two is represented by this vertical line labeled D, or the heat of reaction, also called the enthalpy of my reaction. All right. And now you can see we've got two different markings, B and C. Now B makes sense if we're reading from left to right, because B is the difference from here up to here. All right. That's why there's that dotted line. It's representing the energy that we started with in the situation where we're reading from left to right, and the difference between that energy and the top of the curve. Okay. Now, on the other hand, so actually I'm going to undo that. I'm going to mark that in a different color. So we know that this is that difference in energy that's represented by B, which is my activation energy, meaning how much energy does it take to activate this chemical reaction from left to right, or the exothermic reaction, which means that energy is being released. Okay. And now, if I'm going in the other direction, just use pink here, then here's the difference, right? Here's where I start. Up there is still where I end up. And that is my activation energy, or the energy it takes to activate the reaction if I'm reading it from right to left. All right. Here we go. My activation energy. Cool. Okay, so we've marked all of this out. We know how to label the energy that we start with. That's our heat of reactants. The energy that we end up with, that's our heat of products. The enthalpy, or heat of reaction, which is the difference between the two, and the activation energy, depending on which direction you're going in. It's the heat of reactants, or the difference between heat of reactants and what we call the activated complex. So I'm going to use a final color. Let me see. I'll use yellow to mark the top. We call this our activated complex. And you can think of that as the difference between the top of the curve and 0. Okay, so I'm going to make one vertical yellow arrow just to describe that. That's the difference between there all the way down to 0. Okay, I'm going to leave that up for a second, and then we'll scroll down. We'll talk about some key things to remember. All right. So now if we head down, there are a few key things to remember. Again, the activation complex, that's simply the height of the peak of the graph. And these reactions can be read from left to right or right to left. All right, and that's why we have two different activation energies. This can confuse you a lot on Regents questions. The key thing to remember that I'm always taking my activation energy to be the difference between my heat of reactants, which if I'm reading from right to left, will be on the right. If I'm reading from left to right, it will be on the left. All right, the difference between that heat of reactants and the top of the curve. All right, okay. And so in exothermic reactions, we also need to remember that our heat of reaction is going to be negative. In other words, if I'm taking heat of products minus heat of reactants, as we can see here, if I'm reading from left to right, E is lower than A. So I'm going to get a negative number for exothermic reactions. Okay, and that's because energy is released during them. So I have less energy in my products than I had in my reactants. Okay, on the other hand, if I'm doing an endothermic and I'm reading this from right to left, A is greater than E. So I should have a positive change in H, or delta H, meaning it's a positive number because I end up with more energy in my products than I had in my reactants. Okay. And so my final task for you in this video is, can you label this correctly? Okay. And also, which term is missing from the labels? I'm just going to give you a few hints. We have A and D marking the beginning and end. And I'm not going to tell you which one the beginning is and which one the end is. Depends on which direction you're reading this this diagram in, from left to right or right to left. But we know what the beginning and end of our potential energy diagrams are when we're plotting out a chemical reaction. We also know C will be one thing, and it'll only change in sign depending, again, on which direction you're reading in, and it is the difference between the right-hand side, or the absolute right, and the absolute left of this diagram. And depending on which one you say is heat of reactants or products, that will determine whether C is a negative or positive number. All right. Finally, B, I'm just going to give you a hint and say that B is the difference between 0 and the very top of the curve. And we had a name for that. So check this out. Keep this resource with yourself. Try to quiz yourself by filling in this diagram or labeling A through D on this diagram. And hopefully it will help you keep all of your terminology straight when you read a potential energy diagram for a Regents question. I hope this was helpful, and I will see you next time.